2 of this Thursday AP Chemistry. This is just kind of a continuation of the Born-Haber cycle. This is in chapter 6 of your textbook. It's actually on page 305 in your book. So it's in the bonding section because it talks about how ionic compounds and covalent compounds, how they bond, okay? So notice this time it's NaCl, and so we just talk about here Na solid, okay, going to Na gas, okay, and then just all the different steps. You can add all these together. They're all basically the same steps, but here's your 2 exothermic reactions where the Na plus and the Cl minus come together. That's called your lattice energy, and where the the Cl goes to Cl minus, that's your electron affinity there. Okay, so this one's a little bit harder to follow than because it's individual steps, but it's just showing that these are all positive changes, okay, versus the negative changes there. But again, it's the Born-Haber cycle for any compound, okay? So the difference then between where we started to where we end is going to be this negative. The reality is that the arrow needs to be pointing down. I don't know why they have the arrow pointing up, because it's a negative value. Okay? So, that's your heat of formation. Anyway, that's just the Born-Haber cycle. Now, what I want to do today is talk about rates of a chemical reaction. If I take this piece of paper out of here, and I take this paper and I light it, it burns very quickly, okay? It's supposed to be a little bit quicker than that. Almost caught me. Okay, but we do it again. Okay? So that paper is burning, that rate of reaction is super, super fast. Yet the exact same reaction taking place here, the paper plus oxygen burning, is going very, very, very slowly. So in this unit, chapter 14 in your textbook, in this unit, we're going to be talking about how do we measure the rate of a chemical reaction and what factors affect the rate of the chemical reaction. So in order for us to do that, the first thing we need to talk about is what is necessary in order for a chemical reaction to occur. Okay? So, this is kinetics. Rates of reactions. So, the first thing we have to talk about is what we refer to as an effective collision. Obviously, in order for molecules, atoms to react, they got to collide with one another. What do you think it means to be an effective collision?
To hit right to cause the reaction.
To hit in a way to where a new substance is formed. The atoms either bond together, something breaks apart, some new things, okay? So an effective collision is a collision between 2 atoms or molecules okay, and I'll put, I'm going way over here, reactants. A collision between 2 atoms or molecules which results in the formation of a new substance. In other words, a product. Okay, so it's just a collision that happens where their molecules, atoms don't just bounce off one another. They bond, something breaks, something forms, something new happens. Okay? So, what does it take to have an effective collision? There are two things that have to happen for a collision to be, quote, an effective collision. You already know one of them. What do we know? Why is that paper not burning very quickly? Low temperature, but what does temperature affect? When we said that reaction is thermodynamically favorable, but nothing happens, at room temperature.
Activation.
Because it has a high activation energy. So the first thing that we have to do for an effective collision is that, I don't like the point that I got on these. See, these are brand new and I don't like them. All right. I can't go away from what, it's something new here.
What's the normal point?
It's a chisel, it's kind of more of an angle. This one's round. But it actually might work better, we'll see. I gotta just be open-minded. All right, so the molecules or atoms, again, it doesn't matter, the particles must collide with enough energy to overcome the energy of activation. And we're always going to call that E sub A. I don't know why I like to capitalize that. I have great respect for the energy of activation. So if we again look at our potential energy diagram, this is reactants, this is products, this is potential energy, this is reaction progress. We're going to have a certain amount. This is my EA. So if we're at a low temperature, these reactive molecules, they bump into one another, but they don't have enough energy. They just kind of go halfway up the hill and then back down. Halfway up, back down. Okay? But if they have enough energy, they can make it to the top. And right here is what we call the activated complex. Sometimes it's called the transition state, because it's transitioning from reactants to products. Right here, the reactant bonds are beginning to break and product bonds are beginning to form. You're right in the middle, right at the top of this peak here. It could go either way. It could fall back and or if there's enough energy, then it can actually make products. Okay? And again, just on this is my delta H of the reaction. Just if we need to label everything. But what we're focusing on now is this activation energy. The higher this activation energy is, the more energy the molecules must have when they collide in order to have an effective collision. That's why every molecule, every reaction is going to be different. That's why reactions go at different speeds. Well, some go fast, some go slow. It's all about how much does it take to get it started. Okay? And we'll look at an example of that. Chapter 14, chemical equilibrium, 16. this again with glasses on. There's a certain graph that I'm trying to show to you. There it is, right there. We look at a specific example here, okay, of the reaction okay. You have this very complicated molecule, okay. This is your cyanide, methyl cyanide, probably methyl isonitrile, okay. Okay, so we have this, and it's being formed into where the carbon and nitrogen are bonding here, the carbon and carbon are bonding here, okay? But that's irrelevant. The whole point is that as we're going up the hill, the molecules bend, they have more energy, they begin, these bonds begin to stretch. Stress is put on. At the very top, notice now that the CH3 is pretty much, you know, kind of breaking away here, and the carbon, this bond is beginning to break, this bond is beginning to form. Okay? Well, I should say that the carbon to nitrogen bond, this bond is beginning to break, and this bond is beginning to form. It's right in the middle between the two. And now, here, as you're coming down the hill, now this bond begins to form. It's still stretched. It's not completely there yet, but once we get to the bottom, then we're locked into place. So when we're looking up here, this is your activated complex. This is your transition state. It's where bonds are beginning to break and other bonds are beginning to form. And so it's right there in the middle. It's that transition state between reactants and products. It always occurs at the top of the peak. Okay? So this graph is on, I know that you guys are going to go and read about it. It's on page 595 in your textbook. Okay? It just kind of gives a good example of the activation energy. We have to have enough energy to get up over that hill in order for the collision to be what we call effective. So that's the first criteria of an effective collision. Now the second one is the molecules must collide with the perfect orientation. So the key word in this one is orientation. Now, I used to think that that was enough. You have to have proper orientation. But in the past few years, when we're grading on the AP test, they didn't give credit. You have to say the second part of this, where reactant bonds begin to break and product bonds begin to form. Okay, so there's only one way in which these things can collide. So if you turn back onto page 594, molecular collisions may or may not lead to an actual reaction. Let me make it just a tad smaller. Okay? In order for these things to bond, we want we're assuming that these are chlorines right here. We need these chlorine atoms to bump into one another. If I'm going to form Cl2 as a product, which this reactant does, this chlorine atom has to hit directly on the chlorine here. If this chlorine comes in and hits anywhere else other than that, then it's just going to bounce off and there's not going to be, it will not be an effective collision. There's only one proper orientation to where when the molecules collide, they can actually form. So right now, there are two factors going on. Number one, most of the molecules do not have enough energy to overcome EA. Okay? Number two is that there are some high-speed molecules in the air, because this is the average kinetic energy, is the temperature. There's some high speed, there's some low speed. Remember our Maxwell-Boltzmann temperature distribution graph. There's some out here at the high speed. So some high-speed molecules are hitting this. But they have to hit in the perfect orientation for it to be an effective collision. So not only do you have a limited number of molecules that have enough energy, you also have just chance and circumstance, just the probability of how did they hit exactly right. So it's taken 40 years, it's hard to say, okay? I'm trying to see if there's a date on anything. 3/5/81, so we're right at 40 years. It's taken, oh God, I'm so old. Taken 40 years for this much of the reaction to occur, because they're just so limited, because both of these things have to happen, not one or the other one. You have to have enough energy to overcome activation energy, and they have to collide in the perfect orientation. Does this make sense here? So obviously the more complicated the molecules are, the bigger and bulkier they are, the harder it is to get that perfect orientation. And so as a result, those reactions tend to go more slowly. Small, simple molecules, where there's just a, just a possibility of a reaction, they go much faster. Just another example of that is if I take, we want to say H2 plus I2 makes a very friendly molecule, the high molecule. Hydrogen iodide. Thank you. I'm here all day. Either that or it's the druggie is the high one. All right. So if I want this reaction to occur, I have my two hydrogen atoms bonded here, okay? And I have my iodine bonded here. But if they collide like this, well then this H is going to go here, but there's nothing on this one here. The reality is that we need them to collide like this. And so at the activated complex, what you're going to end up getting is this bond beginning to form and these bonds beginning to break. So this is your activated complex. Okay, where it's somewhere right in between. The hydrogen to hydrogen covalent bond stretching and bending. The iodine to iodine covalent bond is stretching and bending. But yet the hydrogen to iodide bonds are beginning to form. But it's only when the molecules collide in this orientation. Any other orientation other than this perfect parallel side to side is not going to result in an effective collision. So then when we go on, then we end up just getting two HIs actually just get formed. So this is reactants, if you want to label. This is your products. So we're comfortable with that? Two things have to happen. You have to have enough energy to overcome EA, and you have to have the proper orientation where reactant bonds begin to break and product bonds begin to form. That is something essential for you to know. Okay? Essential to know for this test and the AP test. Big concept. All right. So now we're going to look at 4 factors that affect the rate. How do we control the rate? Make it go faster, slower, what do we do? Okay? But everything that we're going to talk about is going to be relating to how does it affect these two things? One, both, You know, one or the other or both, okay? So, what's the first way we can make, the most obvious way we can make a reaction go faster?
Increase the temperature.
Increase the temperature. Okay, now you guys have these notes on down here. Okay? So we're gonna say now 4 factors that affect the rate of a reaction. Number 1, temperature. Now again, I'll try and stay. When we're looking just at this potential energy diagram, reactants, products, you don't have to redraw it, you already have it drawn. I'm just gonna be referring to it, so I wanna have it. Okay, so what does increasing the temperature, in terms of those 2 things, what does increasing the temperature do?
Increases the movement, so there's more.
Increases the movement, so what is it? So kinetic energy is a measure of, temperature is a measure of kinetic energy, and kinetic energy is energy of motion, right? Heat them up, speed them up. You're giving them more energy. What does that mean about the number of molecules that can make it over EA?
It's great.
We're gonna come back to our favorite curve, our Maxwell-Boltzmann temperature distribution curve. Here's the T1. This is number of molecules. Okay, this is energy, speed. Okay, let's just arbitrarily say, that you have to have this much energy to make the reaction occur. So that means that only this small fraction of molecules can actually have enough energy to make it up over the hill. We're not talking even about proper orientation or anything. It's just only this small fraction can make it up over the hill. But if I increase the temperature to some new temperature, T2, okay? Probably a little fat, but you get the point. Now look at the percentage of molecules that have enough energy to overcome EA. Many, many, many more. Notice the activation energy isn't changing. We're just giving the molecules, they're going faster. I always think about this. Were you guys even alive for Snowmageddon? You were, right?
Yeah.
You were in probably elementary school?
5th grade.
5th grade?
Yeah.
So you have to spend the night at the school?
No.
You got home?
Yeah.
Okay, we did. Okay? Now, I was fortunate in that, this is gonna sound weird when I say I was fortunate, but I have an autistic nephew. And he was going to school here at the time, he was in high school, and he was freaking out of why can't I go home and all this. So we had a family friend that lived right here in Millbrook, Colin Mill, I'm pointing the right way,
Yeah.
somewhere over here where you're coming in the back entrance. I'm wrong way, Jose, I always point in the wrong direction, but Millbrook, right there off Colin Mill. So we went, I got permission and we went, and I don't know, there are 4 people in that family and all 4 were stranded at different points in the city and they couldn't get home that night. But they left their garage door open. Who leaves with your garage door open? Anyway, but I'm thankful because we were able to get in. So we spent the night there, but I said, man, I need to get up early and beat the traffic because it's gonna be chaos out there. So we got up, early, like 6:30, 7. Man, I looked like a war zone out here.
Mhm.
But I went and I waited in line everybody's having trouble getting up the hill on Valleydale by Coles, because it was just solid ice. And I waited in line, and there were a couple of 4-wheel drive trucks that were pulling people up the hill, and I was just in line waiting for that, and then the trucks just disappeared. Then all of a sudden, this 18-wheeler comes flying by on the left lane. He goes halfway up the hill and then starts sliding backwards. And so I said, okay, Joe, we're gonna take a different route. So I turned around and I went through Inverness. And there's a pretty steep hill there.
Mhm.
And when I was coming up on that hill, I saw a car that was scared of the ice, and it was trying to ease its way up the hill, and it was just kind of doing and not making any progress. And I grew up in the north, and I knew better. So I said, hold on, Joe. So I really punched it, because you got to have that momentum to get up over that hill. So I went flying by. I said, wave to him, Joe, as we go by. And I mean, we started skidding at the top, but we made it to the top. We got to that, activated complex. We made it, and then once we got there, then it was easy sailing the rest of the way home. Okay? So that's what I think of when I think of this energy of activation. You have to have enough energy to make it up that slippery slope in order to be able to get over the top. If you come in too slow, you're just going to kind of slide back down. They're just going to bounce off of one another. The electron clouds repel, and they just go flying off. Really, what you have to have is enough energy to overcome those electron repulsions. Okay? So that's the first thing. Temperature. Now, so temperature. So an increase in temperature will generally increase the rate of the reaction. And there's two reasons. We've talked about one. Now, general rule. This is not a for sure every time, but a general rule. An increase of 10 degrees Celsius is equal to 2 times the reaction rate. Okay? So in other words, just 10 degrees makes it go twice as fast. You increase another 10 degrees, another twice as fast. Now, so there are two things. Number one, higher temperature means more molecules have enough energy to overcome EA. And that's where we say use Maxwell, Boltzmann temperature graph. I won't say this distribution temperature graph to explain. That's this. Okay? EA is going to stay the same. As you increase the temperature, you just have more molecules that can overcome EA. Okay, so you understand what I'm saying here? This is the Maxwell-Boltzmann temperature distribution graph. We've done it a bunch of times already, but this is where it really comes into play. Now, what else does temperature do?
Makes the molecules go faster.
So how would that affect the rate other than giving them over EA? What's the other factor?
The orientation.
Orientation. If they're going faster, what does that mean about the number of collisions?
It's increased.
More collisions. What does that mean about the probability of having proper orientation?
It's
It's higher. So this is going to be a long one, but we're just going to go with it. So number two, an increase in temperature equals molecules moving faster which increases the number of collisions between molecules which increases the probability of the proper orientation where reactant bonds begin to break and product bonds begin to form. And you have to have this last phrase. It's just going to be something that you're going to have to keep track of. So temperature, an increase of temperature means the molecules are moving faster, which increases the number of collisions between the molecules, which increases the probability of the proper orientation where reactant bonds begin to break and product bonds begin to form. Okay? So temperature affects both. That's why temperature is the most effective way to increase the rate of the reaction, because it helps EA and it helps having a better chance of having proper orientation. All right. I'm going to leave that graph up and I'm going to go to number 2 over here. How else can we increase the rate of a chemical reaction?
Surface area.
Okay? Surface area. Increase it or decrease it?
Increase.
Increase the surface area. Equals faster reaction rate. Why? In terms of our two things, will the surface area affect how much energy the reactants have? So what's that have to affect?
The orientation.
So why will surface area increase the chance of proper orientation?
There's more molecules to hit. Does that make sense?
Okay, keep going with that.
With the increase in the surface area, I don't know how to explain it.
Any help, Ben?
I don't know, I guess there's like more.
Like molecules available to.
Yeah.
That's right. The greater the surface area, the more that get exposed.
Yeah.
So it's going to increase the number of collisions at any given moment. Okay? So the increased number of collisions, so now we don't have to say this, we need to just kind of put a little asterisk by this little phrase. Okay? But an increase in surface area increases the number of molecules that can collide. Okay? So an increase in surface area allows more molecules to collide at any given moment, which increases the probability of the proper orientation. And then I'm just going to say dot, dot, dot. But you have to include the rest of this phrase. Okay? It's the same thing. Anytime surface area, anytime you're dealing with more collisions, it's always going to be which increases the probability of proper orientation to where reactant bonds begin to break and product bonds begin to form. anytime you're dealing with energy, it's gonna have enough energy to overcome the air. All right, what's another one?
Catalyst.
A catalyst. What does a catalyst do?
Decreases the activation energy.
Okay? Okay, it speeds up a reaction by providing an alternate pathway for the reaction to occur which has, as Anna just said, a lower activation energy. So in a nutshell, catalyst lowers the activation energy, but it provides a different pathway. We're gonna talk about this alternate pathway at the very end of this unit. It's gonna be called a reaction mechanism, okay? When we talk about pathway, it's just gonna be a different mechanism with lower EA. So if I'm gonna draw that into here, it doesn't change the energy of the reactants. It doesn't change the energy of the products. It simply lowers the activation energy. So this is with the catalyst. Okay? So delta H doesn't change, delta G doesn't change, entropy doesn't change. Okay? We're just changing the activation energy. We're making the reaction proceed faster. Now, a couple of things about a catalyst. The catalyst will not cause a reaction to occur that is not thermodynamically favored if it's not a negative delta G. If it's not a negative delta G, it doesn't matter if you had a catalyst or not, it's not gonna happen. So catalyst will only speed up a reaction that will already happen. It just, if it's happening very, very, very slowly, a catalyst will help speed that up, okay? Secondly, there are two types. We can have a heterogeneous catalyst, or we can have a homogeneous catalyst. What do you think? Well, hetero means different. So reactants and catalyst are in different phases, different states. Okay? One's a solid, one's a gas. This happens a lot with gases. Okay, you don't generally add in another gas as a catalyst. If you, in your car, you have this thing called a catalytic converter, which is supposed to speed up. When you have exhaust, you make carbon monoxide, which is bad. And so there's air passing, they pass air out, it's got little air gaps in it, so air is able to flow over it. The catalyst bed, which changes the CO to CO2, but it's gotta go fast because that exhaust is coming through there very quickly. So it speeds up, but it's a metal surface. It's platinum, palladium, rhodium. They're highly expensive metals, which is why people go and steal catalytic converters and try to recycle the metal, especially like an SUV, you can crawl under it without having a jack. So they come in just with a saw and they just cut it out and then run away, okay? Because it's got the heavy metals in there, okay? That happens all the time. They made it now to where at recycle plants, they gotta kind of prove where they got the metal because so many people were doing that. But I even just saw something on the news not too long ago where they were having that problem like at a mall or something. But so the reactants are gases, but the catalyst is a metal. So they're in different phases. Whereas obviously a homogeneous catalyst means they're gonna be in the same phase. Okay? Then you could probably even just rewrite that same phase and it'll make sense to you now. All right? There's one more.
So like, heat would be just increasing temperature and not be a catalyst, right?
Right.
Okay.
Catalyst is an actual substance you add.
Okay.
Okay? Anyone know what the fourth one?
I read it this morning, but now I cannot think of it.
Begins with a C.
Concentration.
Concentration. I was gonna say, concentrate, you can figure out the answer. Concentration. An increase will generally increase rate of reaction. Oops. Why do you think? There are two factors. Is concentration going to affect our energy at all? So the only thing it can do is orientation. Why will an increase in concentration increase the rate?
More molecules
What about more molecules?
to collide.
So you have more collisions, which,
Increase the probability of the proper orientation.
okay, which increase the probability of proper orientation to where
The
reactant bonds begin to break and product bonds begin to form. Okay? So, because it results in more collisions, and then I don't know if you want to go dot, 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 but more collisions increases the number of collisions once we get to here, which you can just follow this exact same thing right here, which increases the number of collisions between molecules, which increases the probability of the proper orientation where reactant bonds begin to break and product bonds begin to form. It's the exact same answer. Okay? So those are the four factors that affect the rate. So that's kind of the theory part of this unit. Tomorrow we'll start in with, well, how do we actually measure the rate of a chemical reaction? Okay? So again, your test corrections, we'll have time for those of you on Tuesday, Friday, we'll have time tomorrow to ask any specific questions. And then they'll be due tomorrow night. And I encourage you to read that Disappearing Spoon. Just read it in bed before you go to sleep. It'll help you sleep, but it's also very interesting. It gives you a little bit about the Born-Haber cycle. It tells you about a little background on Fritz Haber. He wasn't a very good person. And so, all right, hope you have a great rest of the day.